You're listening to the Platform Engineering Podcast, your expert guide to the fascinating world of platform engineering. Each episode brings you in-depth interviews with industry experts and professionals who break down the intricacies of platform architecture, cloud operations, and DevOps practices. From tool reviews to valuable lessons from real-world projects to insights about the best approaches and strategies, you can count on this show to provide you with expert knowledge that will truly elevate your own journey in the world of platform engineering.
Welcome to the Platform Engineering Podcast. I'm your host, Cory O'Daniel. Today, we have a very special guest joining us to discuss Kubernetes' place in the history of cloud operations. Brian Grant was the original lead architect of Kubernetes and has been a key figure in shaping the project and the broader cloud-native ecosystem. Brian, welcome to the show.
Hey, thanks for having me.
Yeah. Before we dive into the fascinating world of Kubernetes, I'd love to learn a bit about your background, how you got interested in distributed systems and container orchestration, and just kind of your journey that led up to the work that is releasing Kubernetes.
Yeah, earlier in my career, 30 years ago at this point, I worked in supercomputing. I worked on a climate modeling project at the Lawrence Livermore National Lab, for example. And so I had some background in that, and then I'd use some queuing systems, LSF, load leveler, that type of thing, in some of my earlier parts of my career. Then I came back to supercomputing and actually did high-performance computing on GPUs way too early. And that brought me to Google through an acquisition. So there wasn't a need for it at the time. So I had to find a new mission that I undertook. And I did that for a while. But then when I was kind of looking for my next project within Google, the container platform, Borg, was looking to bring in some new senior tech leads project. The creators of the project, Borg started around 2004 into 2003, and most of the creators of that project had moved on to other things because that was the way. Google was growing crazy fast, and so I and a few other folks came onto the project and started looking at what needed to be improved. So the initial thing I did was related to what I was doing before that, which was making the code more multi-threaded so that it could scale with the increasing core counts, more sockets, more cores per socket, and the data centers and that kind of thing. And as part of doing that, I analyzed how Borg was being used. Like what requests was it receiving, what kind of workloads were running on it, what were people doing with it, and found that it was being used in ways it wasn't really designed to support.
Yes, love it. We love it when they do that, right?
Yeah. So after not too long, I started an R&D project called Omega to re-architect Borg. Initially, the plan was to extract pieces from Borg and redesign them, but for various reasons, we ended up kind of exploring more broadly. And some of those ideas were eventually factored back into Borg, but after about 5 years of that, cloud was becoming increasingly important as a priority, and the focus was shifting in that direction. So 2013 is when that really started to escalate. So just in terms of level setting, Google Cloud had App Engine for a few years by then, and Google Compute Engine, the infrastructure as a service product, had been developed over the preceding few years and was approaching general availability. And Docker emerged at the same time.
Yeah.
So that is how I kind of got into that whole side of things. Is it just so happened that I just spent a few years doing R&D and how to build such a system.
Yeah, and so like this is all happening at the same time. Like big clouds exploding, services are like more and more services are getting spun up. Containerization's coming onto the scene. The initial release of Kubernetes now 10 years ago.
Yeah, and Borg just had its 20th anniversary.
Wow. So when was as you're working on Kubernetes, when was the moment where was it always designed to be open sourced, or was there a very specific point in time where
No, actually, initially we went through this phase where our group was put together with a couple of directors from cloud and from our internal infrastructure teams it's called the Unified Compute Working Group. And the original charter was to figure out something that was more flexible than App Engine, which was just platform as a service, and lighter weight than virtual machines and compute engine, something nominally more Borg-like that Google itself could run workloads on eventually. Because Google had kind of skipped virtual machines and had never really run workloads on virtual machines. We'd used raw machines and then containers, working on developing C groups in the Linux kernel and such. Around the time I started Google, C groups were rolling out within Borg. So we kind of skipped the whole VM wave, and there was kind of no going back to that. So and Google has a culture of trying to unify all the things. So the idea was, well, how can we create this flexible container layer as a cloud product? So there were several proposals for different ways we could create cloud products along those lines. So I would say between August and November, and those proposals kind of continued into the spring as well. But really, it was just getting started in that August to November time period. And that's also when I was sketching the initial API. So the open source angle didn't really come in. I was actually looking through my notes prep for this recently. Didn't really come in until like the December timeframe.
Okay.
And there were a bunch of reasons for why open source was proposed, and actually over time, even more and more reasons continued to occur to us about why it made so much sense for us to do that. And December is when GCE reached GA as well, just coincidentally, or maybe not coincidentally. But so Google Cloud was just kind of starting its journey at that point in time. Just the proposal to make it open source really made sense to all the people who were involved. Docker was open source, Mesos was open source, and that was kind of the leading execution runtime for larger deployments for, especially on-prem deployments at the time. And it actually had some overlapping history with Borg as well. So all the open source competition was very much on our minds at the time. And also Google had a history of writing academic kind of papers about MapReduce and Chubby and the Google file system, et cetera, et cetera, et cetera. And open source projects emerged copying those systems.
Yeah.
So we talked about Hadoop and getting Hadooped, which would, it's like we come out with the idea and someone else builds the popular open source project. And certainly we wanted to avoid that. And but we did want to enable our customers to be able to take advantage of whatever we built and run on Google Cloud and reduce the friction for running on Google Cloud. So I think we talked about in the Kubernetes documentary the rationale for this, but obviously at the time we had close to zero market share because it just launched, and we felt the need to really kind of more disrupt the space and shift the entire industry towards containers, which I think Eric Brewer talked about when we open sourced Kubernetes at DockerCon.
Yeah.
Because we had a lot of experience with that model, and we knew a wide variety of workloads could run really well using containers. For the folks involved, we felt strongly that it was definitely the way to go. That is, containers in general and open source specifically. So it took a while to get agreement that that's what we were actually going to do, and that agreement came very late in the entire process. But it just made sense for so many different reasons.
Yeah. Was this Google's first big open source initiative? Like you said, that there was a lot of academic papers.
No, actually, we actually went and talked to a number of the other open source efforts. They're all pretty different. So like Angular was open source.
Oh yeah, that's right.
Chrome and Android were open source, and Golang was open source. So Google already had thousands of open source projects, some of which were very widely used and very well known. But for what we were trying to do with the Kubernetes project, they all seemed very, very different in their flavor. and how the projects were run and what they were trying to do. Like in terms of building community around the project, a lot of these projects didn't really try to do that in the same way. So we were really treading new ground there, especially as the project grew once we open sourced it.
Yeah, and it seemed like it was pretty quick that you started working with other organizations, CoreOS, et cetera, like being involved.
I think Clayton Coleman at Red Hat started sending PRs within a week or two of of open sourcing it. And I think within a few weeks, we had doubled the size of the effort, more or less. And then by February, there were dozens of engineers working on it with it, across the community.
Yeah. When was the first point where you realized that this was going to be as big as it, or it had the potential to become as big as it has become?
I don't know that there was a single point. We were so busy just trying to stay ahead of the competition. We did watch the other open source efforts, the other commercial products very closely, and tried to figure out what users needed, what appealed to them. So I think that was one of the great things about the open source projects, which we predicted, but it did work out, that it brought us much closer to users really early on. And, we could meet their needs much faster, partly due to their direct contributions, but also just the open feedback. And we took a lot of cues from Docker, give them a lot of credit in terms of how to run a community. They had an IRC channel. We created an IRC channel. They had regular meetings. We started regular meetings. So we really learned a lot from them in the early days, I would say, in terms of how to engage a community. Later they kind of diverged and we became our own thing with special interest groups and working groups and the steering committee and whatnot. But it was really very informative in those early days. First, little more than a year, Kubernetes reached 1.0 in July 2015, and that was because we set that as a milestone when we created this cloud native computing foundation for the project. So that milestone was set, don't remember exactly, somewhere like March or April 2015. And we worked hard to hit that milestone, ripping out features and things like that, postponing them in order to hit it. And then, we watched the competition. Docker released the kind of Swarm v2 is how I think about it, at DockerCon 2015. That was still no control plane, just a command line tool.
Yeah.
So not too worried about that, because we knew from board how powerful the control plane could really be. But, the following year when Swarm launched a control plane with Swarm mode, that was more of a concern. So, we tracked those sorts of things very closely. Mesos, we worked together with Mesosphere on some areas and, to some degree competed for users, but it didn't come up as much because, especially at the beginning, Kubernetes was considered to be smaller scale and Mesos was considered to be large scale. So we're targeting very different kinds of users.
Yeah.
So I'd say by the end of 2017 is when it became really clear that we were doing something right.
Yeah.
Because I think by the end of 2017, Kubernetes was everywhere. Like, it was ubiquitous. Amazon had a product, Azure had a product, Red Hat had a product, VMware had a product. Like, everybody had a product.
And was there coordination with the other clouds around their products, or they just saw the potential in it and they just started running, or was it?
There was no real coordination there. I did start the Kubernetes conformance program to mitigate the potential of fragmentation as more and more products were created. That was something I was very concerned about. I wouldn't want, someone to fork Kubernetes and extend the feature set in an incompatible way, or to freeze the feature set and make it difficult for us to continue to improve the project. So we took some lessons learned from some other open source efforts. We looked at how OpenStack and Android and some other, literal standards approached the conformance problem. Because really, in retrospect, the problem we had is very similar to a standard, like Wi-Fi is the example I use, where if you have a lot of vendors creating Wi-Fi routers and a lot of vendors creating Wi-Fi clients, effectively, Wi-Fi devices that need to connect to the routers, they all need to interoperate seamlessly.
Yeah.
Right? So the only way you can do that is by having a really clear, solid, comprehensive spec that both sides can implement and validate that they meet that spec. And that's essentially what we needed with Kubernetes, where we wanted an ecosystem of management tools and workloads and everything you could imagine, just work on any Kubernetes clusters to the extent possible. So that informed how we treated the conformance program using a testing-based approach. So it wasn't fully specified in terms of all the interfaces and whatnot, but we created a suite of tests that would be executed against a Kubernetes cluster to ensure that it behaved as expected.
Yeah.
Kind of end-to-end tests. And in order to prevent the problem of getting frozen in time, we moved the goalposts deliberately. So, your conformance is only valid for about an amount of time in the duration that the Kubernetes releases were considered supported. And, you have to recertify with new releases.
Nice. And then we also have the operator model and custom resources. Was that planned as a part of the original API design to be able to extend and kind of extend how Kubernetes works, but in a Kubernetes native way? Was that part of the original design, or is that something that kind of...
Yes and no. So I knew from the experience with Borg and Omega that we needed an extensible concept space, is what I call it, because Borg had a very rigid set of concepts that were baked in. It had jobs, tasks. Actually, tasks wasn't even a real resource in the way you would think in terms of the cloud. So it had jobs, Alex, machines, packages, and it couldn't really be extended. So what I would see projects do is things like batch job admission and Borg cron job scheduling and a variety of other systems, auto-scaling, were built as separate systems, kind of bolted on top, and they would pull for information. And if they needed additional information to kind of drive their behavior, they didn't want to create another database or another store that had to store the state. So they asked for ways to extend to the Borg API to put in their configuration effectively. So that was pretty ugly. It worked, but it was pretty ugly. So I wanted a way that we could add these as first-class resources effectively. But in the beginning, we were just trying to build something to run containers. So we just had to get that out really quickly and put that together. It was a sprint to get all that done by 1.0. So it wasn't until after 1.0 that third-party resources were created. And we had a couple of different kinds of extensibility we needed to support. For example, we had some use cases where we needed to support APIs that were not backed by etcd. So we actually created that mechanism first, resource API. This is the API aggregation mechanism. And the API aggregation mechanism ended up being used to create custom resources later.
Okay.
But the initial implementation of third-party resources came after 1.0. It was at the point where 1.0 only had replication controller in terms of workload controllers. But we knew already that we needed to have higher level deployment objects, daemon sets, jobs, cron, etc. And that was going to create a bunch more resource types, and we were worried about where to draw the line. So in particular, we debated, should cron be a built-in concept or not? So that is kind of what started to spark the idea of having a first-class mechanism. We didn't set out, let's build a control plane that can control all the things. That wasn't the main goal. But, we did know that there was this large ecosystem that needed to exist for the different kinds of workloads and automation that people would build. Once we put third-party resources and then custom resource definitions out there, I would say operators were not something that had really come up in terms of building workload-specific operators to automate, Kafka or to automate a specific kind of database or something like that. That wasn't really the intended purpose. I mean, it's pretty interesting to see what people ended up doing with it, or things like crossplane or configure infrastructure. So yeah, I guess I would say in terms of, we knew we would need to be able to easily extend the API. Exactly how we would do it, I would say we didn't do premature generalization. We generalized it at the point where we thought we were getting close to where we wanted to draw the line.
Yeah.
We still added a few built-in resource types after creating CRDs. Like in particular, we hadn't implemented binary encoding for CRDs yet, and there were some, like the least resource, we were worried about it being not efficient enough if it were just JSON. So we made that a built-in resource type. But at least we had that release valve where we could say, let's just at least first implement things with custom resources.
Yeah. And so you weren't just involved in building Kubernetes itself. You also had a lot of impact on how the tooling to interact with Kubernetes was designed. You worked on kubectl, customize, and at the same time Kubernetes is coming out. It was the same year Terraform's coming out. They both have this declarative model of managing resources. What led you to the declarative model? What was the motivation behind that?
Yeah, so within Google, Borg and many other systems are all configured declaratively. Borg uses a language called Borg config, which is ended up being generalized into a more general config language. It's very similar to Terraform in many ways. It's less extensible. So, it's built to be specific to Borg and Borg's APIs. But in many other ways, it's very similar. It's a domain-specific language for generating configuration for Borg. And there was a lot of configuration written in this language, millions and millions and millions of lines of configuration. And it seemed excessively complex, and it was hard to extend the set of tooling around that. So I wanted a clearer contract between the system and the tooling to make it easier to build tooling. And in particular, things like auto-scaling created special case diff code in the tool that it would just have to know that, this field of this resource is going to change because some other system might tweak it. And that's not really a very scalable approach.
Yeah.
Terraform has the same problem. Terraform is very intolerant of drift of that kind. So there were a few principles I had in mind from the beginning. You can see this in PR 1007 in the Kubernetes repo. I'm notorious for remembering the early issue and PR numbers, by the way.
I love it.
Where I kind of wrote out my current thoughts at the time about how it should work. And early on, we had this idea that resource representation in the API would be the serialization format for everything. You would just be able to literally just serialize the API resources and use that for declarative configuration, use it for disaster recovery, use it for storage in etcd, use it everywhere.
Yeah.
And that was a brilliant design decision, I have to say. That worked awesome. That just worked fantastic. And I still think it's proven over 10 years that it was a fantastic decision. So we knew that had certain consequences, like we needed to have the resources be self-describing, right? So this is why the API version in kind is in the body of every resource, even though it seems redundant with the REST path. It's so what? It's redundant with the REST path. But that means if you have a representation of that on disk, the client tool can figure out what API to call from that representation without any external information. Mm-hmm. You don't need a client-side provider layer of the kind that's in Terraform. You can actually just have a very simple client, a script even, that just extracts that information and curls the API, and you're off to the races.
Yeah.
So that was very empowering because you could do things like run imsept or sed or some simpler Unix tool over your config and then pipe it to curl or whatever. So with kubectl, our initial command line tool was called cloud config, which was then renamed to kubeconfig, which was then replaced entirely by kubectl. And with kubectl, we had a bunch of goals of making the foundation more solid and whatnot. But one of the things I really wanted to set up is support for declarative configuration in the future. And a key aspect of that was a model for bulk operations. So instead of the G-Cloud model of putting the service name or the resource name first, and then the verb after, and then the argument specific to that imperative operation, the way kubectl works is the verb is first, and after that come the nouns. And in some cases, it could be a specific noun like kubectl create config map blah blah blah. If you need to do something kind of imperative and very specific, but you can also just pass files, and those files can contain resource types that are heterogeneous, and any number of files and any number of resources. So that pattern reinforced the consistency across different resource types in the API, and paved the way for these bulk operations being able to manage multiple resources all at the same time, because every use case in Kubernetes, every use case in cloud pretty much involves several resources at least, right? Like, in Kubernetes, a service and a deployment, or ingress service and deployment, or ingress service deployment, config map, horizontal pod autoscaler, et cetera. So apply, we started working on and realized, well, it had some tricky aspects. So actually Sam Godes from Box wrote the initial kubectl proposal and worked on that with us, and wrote the initial kubectl code and started figuring out, okay, what is it going to take to be able to do apply? And with apply, I really wanted to solve this problem of special case diff code. And we didn't really entirely solve it until server-side apply, but this idea that fields in resources might get populated automatically, either because they're defaults, or they're set by a mission control, which came later, or they're set by an asynchronous controller, like autoscaler is the canonical example. We wanted to be able to be tolerant of that. So, you could specify a subset of the desired state and have that enforced declaratively, but you didn't necessarily have to control the full desired state. You could interoperate with other automation. So that was a key part of the design, because I just saw so many special case hacks in Borg where that was not considered, whether it's horizontal autoscaling or vertical autoscaling, or setting security settings, or automatically plugging in some application config values, or whatever it is. I felt strongly that there was no hard line where you could say, oh, these things are going to be set by automation, and these things clearly will never be set by automation. Like, I just did not believe that was good. Anybody would be able to draw that line in an accurate fashion. So I wanted a more general mechanism that could, what Daniel Smith called it is, having merging intent from both humans and robots, basically.
Yeah. I mean, there's two actors on the system, right? I mean, that's one of the things that's still, painful with other declarative, state models like Terraform. Like, something will make a change to the system, and now you have drift, right?
Right. So, that eliminated several classes of drift right there by doing that. And, also looking at where we drew the line differently from Terraform, informed by the experience in Borg. I did not want client-side orchestration to be required for as much as possible. Like, you do an apply on the client side and let the controller sort it out. So, you can create pods referencing containers that haven't been pushed to your container registry yet. And the kubelet will, give you image pull back off for a while, but, it will keep retrying. And when the image shows up, it will be able to pull it. In general, we wanted the system to be resilient in that way, because things go up and down, or take time to propagate, or get applied out of order, or whatever. And I wanted the system to be tolerant of that. So that's was a principle we enforced across all the initial controllers. There are some things that didn't entirely respect it later on, but for the most part, yeah, you can just do kubectl apply, and ordering doesn't matter, and timing doesn't matter. You don't need a heavy client-side orchestrator, and it just works.
Yeah. So Kustomize is an interesting one. I'm a Kustomize fan, and I feel like Kustomize does not get the love that it should have. And I don't know if it was just that Helm had gotten such a foothold at the point in time that Kustomize was coming out. But what do you think? What is your take on Kustomize versus other ways of managing resources? And is there anything that you think that maybe the community at large just like misunderstood about the customized model?
Yeah, I can talk a little bit about that. So with the success of making it relatively easier to build tools and having this clean contract between the clients and the servers, there were lots of tools, like hundreds of tools. Helm definitely became the dominant tool, and I brought Helm into the Kubernetes project. We had another team at Google working with the Deis team on Helm because we did need that ecosystem of components of off-the-shelf applications that Docker had, that Ansible had, that Chef had, that Puppet had, and that was, kind of a proven way to do it. So, they were off working on that, but, looking at the complexity of the Helm charts, we had discussed several different templating options in kubectl, and also features like declaratively specifying multiple files and declaratively generating config maps from application config. And so the original customized KEP mentions, I think, around a half dozen of these kind of long-standing user requests that we were pondering how to best support. So the idea for customize was just that we should just have a kind of a simple out-of-the-box tool for solving those basic declarative configuration needs for people using the Kubernetes project, because people using Kubernetes would at least have, like a development environment and a production environment, or they'd need to redeploy the same new versions of their image to the same deployment, or update their config maps, things like that. So we just wanted a super simple tool for those basic workflows without having to learn JSON or Starlark or, some other much heavier weight solution. I didn't want to go the direction of board config. I really resisted officially blessing any of those domain-specific languages. And Customize felt like it could be Kubernetes native. We could use the Kubernetes patch mechanism, much like other commands in kubectl. We could know where the image field is in the deployment resource and could just go change it for the user. We could understand what config maps were, and just like kubectl create config map imperative command, we could do that declaratively. So it really felt complementary to kubectl, and it could solve a bunch of these simple use cases. It wouldn't solve the problem of off-the-shelf workloads, but if you are just building an app and you want to run it on Kubernetes, it felt like it could solve those common cases. So originally, I think it was called KExpand. It was my proposal for it was in this really long document that some people called the damn Bible, the Declarative Application Management Bible. But that document is still in the design doc archive in the Kubernetes repo, or the community repo, I think it is, or the one of the repos. So that proposal was kind of extracted out of that document, and Jeff Regan built the initial implementation. And I really liked the ergonomics of it. It was simple. It was YAML. Patching aspect was really heavily emphasized, which I think was unfortunate. The built-in transforms, like to set the images or the replicas, I think are super useful, and more of those could be added potentially if there are super common transforms that people need to do that they want to kind of a simple shorthand to specify declaratively to go do that. But that's really what got me thinking about this idea of configuration as data, but actually just manipulating the configuration data.
Yeah. It still feels like to me, honestly, like if you're not grabbing off the shelf stuff that you need to like highly customize, it feels like the easiest way of getting an application, especially if you have multiple environments you have to deal with, like today. It's still my preferred tool, but it is like, it's one of those things I feel like on Teams, it's like, well, we're using Helm for this and this and this and this. Like, why don't we just kind of suffer through Helm for this? And it's like, well, there's another tool that we could use. It's just a bit easier.
Yeah, and one thing that I found interesting is, the recent discussion about the rendered manifest pattern, where people are rendering out their configurations, their Helm charts in advance to understand what is actually generated. And customize, in my opinion, if the things you need to customize are relatively minor, customize just makes that more obvious.
Yeah. So, we're 10 years in. there's a lot has changed over the years in Kubernetes. A lot has changed in the cloud space. Like how, with different Kubernetes steering committees, which you're also a founding member of, like how have you been able to approach evolving the project while maintaining this original architectural consistency? Like as more companies are coming on, more organizations, right? I've heard that like it's even getting like interesting now with like how we abstract away the compute, but now like GPUs have different profiles that we kind of have to like take into consideration. So how have you maintained that while also making the project so easy easy for us to evolve?
Yeah, the steering committee actually came relatively late in the project. We formed the Bootstrap committee in 2017. For the folks involved with the project very early on, we kind of knew who the deciders were amongst the people working on the project, and that wasn't really any debate. Then once the project was growing and we started to formalize that into special interest groups, some of that became more formal. We also created a review concept of reviewers and approvers, because Kubernetes mostly started with a kind of a monorepo. We had to subdivide ownership of the repository. This is before GitHub and GitLab had co-owners mechanisms. We built our own, inspired by Google's internal owners mechanism, and started distributing ownership of the code base that way. Kubelets, API server, API, etc. Kind of giving approver rights to the people who had the most domain knowledge about those areas and who'd been leading those areas pretty much since the beginning of the project in many cases. Eventually, we had to figure out how to bridge the SIG structure of incorporating the community with that reviewer approver structure. So I created this concept called subproject, which would be subprojects of SIGs, where the subprojects would have reviewers and approvers and have ownership over particular parts of the code base. So I think that part worked really well. When we formed the steering committee, we felt it was very important for the steering committee to be responsible for certain aspects of the governance of the project, but not the technical governance.
Interesting.
So the steering committee is by election, and we did not necessarily want to put, like the technical decision-making power into the hands of an elected body who may or may not have the experience or the expertise with the project.
Yeah, that's interesting.
So I created SIG architecture to hold that power. We had kind of an explicit delegation of that responsibility to SIG architecture, to decide those high-level project principles, things like the API conventions. We created this production readiness review effort to ensure that new features would be sufficiently observable and reliable and tested and things like that. The conformance program was put under SIG architecture's purview as well, to kind of define what is the expected behavior of Kubernetes and maintain that over time. And the key technical deciders of the project who are reviewing. So we also developed this KEP process, the Kubernetes enhancement proposals. We had an informal design documentation process since the very early days of the project, as we brought in more and more people. And so that was formalized into this KEP process. And, so the people who would review those KEPs would be the technical deciders for those areas. So that would give the opportunity for broader review within the project, since there's a process for kind of publishing the KEPs and a period for reviewing them. But, also ensure that things got reviewed before they got added to the code base. As it so happens, we also started pushing code into extensions with CRDs and other repos. So we let the SIGs kind of create their own repos in the Kubernetes SIGs organization on GitHub, and experiment with things, because we didn't want to actually block progress, but we just kind of, if they're going to be in Kubernetes by default, then we wanted to have a higher bar. So I felt like that part of the process worked pretty well. Also, like Customize started in one of these CLI repo as a totally separate tool before it was brought into Keep Control. But yeah, over time, and the project has matured, has slowed down, has a huge ecosystem around it. So, you don't necessarily need to be in the Kubernetes project to create functionality related to Kubernetes in your own project, in your own tool. And sometimes that's even better because as a standalone project, to some degree, you can have your own brand, you can have your own, make your own decisions, have your own community around it. Under the Kubernetes umbrella, the project's so huge, things can get lost or drowned out. Kubernetes releases have always been pretty big, but things can definitely get lost in the noise there. I don't know how many all-time contributors there were now, but as of like 2018, 2019, I think there was around 50,000 all-time contributors, which just seems nuts.
Yeah.
But one thing it was kind of nuts, but we had a strategy to try to engage the community through contributorship. And there's always this tension about how do we actually manage the volume? Do we really need more contributors? How can we ensure that it doesn't overwhelm the maintainers? So that was always a delicate balance. But I think at one point, something like 12% of users had contributed.
Yeah.
Which I felt like was a success, that strategy was working. And, I think the IKEA effect did build a number of advocates, even if people just fixed documentation or wrote new documentation. Like I wrote the user guide. Documentation is totally necessary. It's totally awesome. That's a valid contribution, right? So, I think it keeps the project in touch with the user base as well as vice versa.
Yeah. And it's just a phenomenal amount of contributors, companies, a massive project that's still evolving, is easy to extend. And like, I feel like the SIG groups they're created around it, like that. I mean, I think that's one of the more phenomenal things I've seen in open source, like just the sheer number of people involved, the size of the project, and how big it is. And it hasn't ground to a halt in like bureaucracy, which is just absolutely impressive. Like there's still I feel like I'm pretty up to date on Kubernetes, and like I'll see a new release come out and I'm like, oh my gosh, I've got so much to catch up on. Like so much came out in this new release. Like it's moving at a cadence still that I feel like many open source projects don't move at.
Yeah, well, software has to evolve in order to stay relevant. Like you mentioned the AI workloads earlier. We deliberately started with just simple stateless workloads on Kubernetes as kind of the biggest segment of workloads that would be easy to get running on a system that would move containers around. And but we had a mission, I guess, to bring a more diverse set of workloads on to the platform. So as I mentioned, at 1.0, we knew already that we would have stateful workloads and daemon sets and batch jobs and cron jobs and so on. At one point we had an effort to get Spark running on Kubernetes. We had efforts to get other popular workloads running on Kubernetes. And AI workloads are just kind of the latest example of that, where, we want those workloads to be able to take advantage of the whole ecosystem around Kubernetes, the config tooling, the CI/CD tooling, the monitoring and logging integrations, the networking and storage integrations, the secret manager integrations. Like all those integrations are a lot of work to do, even individually, much less the aggregation of all of those things, policy enforcement, et cetera. So, I do think there is benefits to running pretty much almost any kind of workload, monolithic workloads, any kind of workload on Kubernetes. So that's why we made decisions like we need to support DNS so that workloads that use DNS to discover instances can run on Kubernetes and instead of having to rewrite those workloads to use a bespoke service discovery mechanism or something like that. Yeah, so I'm hopeful that the community will rally around the best way to make GPU-based workloads, for instance, run on Kubernetes. That'll just be kind of the latest example of an important workload that has been made to run on it.
Can you just maybe elaborate a little on like what is different about like what we're seeing in AI and ML workloads that is kind of different from the workloads that we're currently running today on Kubernetes, stateless or maybe even stateful workloads?
Yeah, I think there are multiple aspects of that. One is how the resources are scheduled and partitioned. So at the beginning of Kubernetes, and actually kind of early in Borg as well, the most important resources to subdivide were just CPU and memory. And with C groups, you can carve up CPU, you can carve up memory. So you just have to find, the scheduler can look for a node that has enough CPU and memory nominally to run that workload. GPUs cannot be sliced and diced in the same way. So if you have an inference workload that doesn't need a whole H100 or something like that, then what do you do? So that needs to be representable in a way that the scheduler can deal with, where it can kind of see what resources are available semi-statically and understand what the constraints are for choosing where that workload can go. So if there are a bunch of constraints like, you shouldn't put certain types of workloads together, or you can only subdivide with a certain granularity, those kinds of constraints, we didn't really have mechanisms to deal with those things. So we have to figure out how to model those. And there are just issues at the kind of the device level and the driver level, figuring out how to partition the devices or to understand what parts are available. There are some reliability issues in terms of detecting, we have this node problem detector that detects certain types of problems, but if we have to look somewhere else to see if there may be some problem with the accelerator on the machine, then that mechanism needs to be extended to do that. So I think the talks at KubeCon EU about dynamic resource allocation and some of these other things that don't entirely mesh with the current model, I think the community will work through that. But it is a new resource basically that has different characteristics from the previous resources. Like CPU is very fungible, memory is mostly pretty fungible. Yeah, the accelerator devices are not as fungible.
Yeah.
And then at the cluster level, training workloads are very different. They're much more like the supercomputing workloads that I worked on back in the 90s. And, where basically there are lots of machines running the same program at the same time that need to communicate synchronously.
These are like all or nothing kind of builds, right? They all have to execute successfully or they all kind of fail.
Yeah. So, I think discussing what the best way is to address those workloads, that's pretty much a totally different problem from everything I just talked about. It's kind of another topic that would need to be figured out. Batch workloads had already been discussed, and mechanisms like Q were being developed to run workloads sequentially if they can't all fit on the cluster at the same time, because if they're continuously running workloads, you just have to do this footprint allocation. If they are bounded in duration like batch workloads, then you can schedule them in time instead of just in space. So those are kind of different dimensions in this sort of new kind of category of workload that has different macro characteristics. We may need to just handle differently at that level.
Yeah.
Some people run their clusters differently, even for just stateful workloads versus stateless workloads. So that they, especially if it's not running in the cloud, if it's running on-prem or something like that. They don't. If there's data gravity involved, then they may need to manage the clusters differently. So I think this is another example of that, where the workload characteristics may change how the clusters are managed.
Yeah. Besides AI and GPUs, what other like new frontiers or unsolved challenges do you see in the cloud native field?
I think the big challenge that people have been talking about for a while is the complexity. Personally, I think it's great that all of these projects are available. Otherwise it wouldn't be feasible for an organization to build their own service mesh and their own policy enforcement engine and their own everything, unless you're at like Google scale or something like that. So having those things available is awesome. Each one does add some operational complexity. So figuring out how to users mitigate that complexity, I think, is an interesting challenge. And part of it can just be in terms of decision process, like how do you decide whether you need this tool or that tool or this other tool, and whether it will have a large enough return on investment that is worth incorporating into your stack. But there are probably other things that could be done to, especially as Kubernetes matures, to ensure that these things don't have excessive operational burden or introduce too much operational complexity. So I think that may be interesting to look at a more quickly than, like on a project by project basis to see if there are common patterns or standards or approaches that could be applied.
Yeah, one of the things I've always found interesting about the complexity problem is like it's definitely there. Like, I mean, jumping into Kubernetes day one is not like an easy task, but like we're getting our systems up, like we're either home growing something or learning something else, right? And I've always kind of considered the greatest feature of Kubernetes a portable knowledge set for me, whether I'm working on my local machine or in AWS or GCP or Azure. Right? I kind of have customers all over the place. Like I have these same set of skills that like I can move, whether it's from cloud to cloud or company to company, right? Like that's always been the biggest benefit to me is like that boon of us all finally being able to like agree on how to operate things and that it would work from one place to another.
Yeah, I completely agree with that. I view Kubernetes as kind of a few years ago at KubeCon, I have a talk about like 10 different ways to think about Kubernetes. One of the ways that I think about it is it's like a cloud in a box. So it's the API was modeled after infrastructure as a service, but it's just kind of operating system level of abstraction instead of a hardware level abstraction. But it's intended to be as equally or almost as flexible as those primitives. There's a compute primitive, which is pods. There's a load balancing primitive, which is services. There's an L7 primitive, which is ingress or gateway. There's a storage primitive, et cetera, et cetera. So yeah, the fact that we could create this kind of cloud in a box scenario, and it's not something that just runs individual containers or just does, one thing or a couple of things like some of the other tools, means that you can have this bigger island of portability across all the different clouds. And maybe if you're on, just locked into one cloud and use all their proprietary tools and services, it doesn't affect you as much. But yeah, when you go to your next job and they use a different cloud, then it starts to affect you, right? Or if you can't find the best of breed tool that you're looking for from that cloud, then it may affect you. So I do think that being able to create that ecosystem and that platform that is bigger than any one cloud is a really valuable aspect. If you can figure out how to run a Kubernetes, a workload on Kubernetes on Google Cloud, you can run one on AWS, you can run one on Azure, you can run one on DigitalOcean or wherever. I think that's really valuable. And from a vendor perspective, it seems like it's beneficial so that you can, integrate with Kubernetes and now it works everywhere. You might do some additional integrations with individual cloud providers, but if you can constrain your scope to Kubernetes, at least initially, that's a pretty big addressable market right there.
Yeah, it's massive. And that's why there's so many people in the space. Sorry, yeah. A lot of startups listen to the podcast. That's why we're all here, right? Yeah. Awesome. So like, where do you see the field heading in the next 5 to 10 years? You've been in the space for a very long time. Like, where do you think is the next big thing?
Good question. Obviously, there's a lot of excitement around AI right now, and that introduces some opportunities that are pretty game changing. So I expect that to continue for a while. Other than that, it'll be interesting to see what happens in the ecosystem, whether some additional standards at the level of Kubernetes emerge or not, in the sense of how widely used they are, because there is a lot of fragmentation right now. I haven't really seen a lot of best clear distributions emerge, which is a little bit surprising. So maybe that will happen, as we'll see some kind of standard distributions of some of these sets of tools on top. I think it was interesting that Glasscube emerged recently. After 10 years, kind of a package manager, in the sense of for managing cluster components has emerged. So yeah, I think that aspect is really interesting when we see more standardization of kind of the higher levels on top of Kubernetes. Not in the sense of application platforms, because that's, I think, always going to be fragmented, but in the sense of some of these other complementary components, whether it's, policy enforcement or GitOps or service mesh maybe,
you've done a ton of work in the space. Kubernetes has obviously changed a lot for a lot of different engineers, operations folk, clouds. How do you hope that your work in Kubernetes will be remembered and built upon in the coming years?
I mean, in terms of building on Kubernetes, I think people have already been doing that. So
Yeah.
I feel pretty good about that. Kubernetes has been used for like things that I didn't imagine, like retail edge. I didn't imagine that Kubernetes would be used in retail edge scenarios and be in like every Chick-fil-A restaurant or things like that, every Target store. I think there are independent, even if you don't use Kubernetes, I think there are some lessons to learn from Kubernetes. Like it drew the line in terms of declarative management in a different place compared to other tools. And I think it just made things just a little bit easier compared to the other infrastructure as code tools, for example. The control planes, I think similarly, where we didn't really set out to build a control plane at the beginning per se, but we did have ideas about how to do it, and now we see people using the Kubernetes control plane for all kinds of things. In some cases, it makes sense, but it may not be. If you were setting out to just build a general purpose control plane that could use for lots of things, you might do some things a bit differently. Like we had very specific constraints in mind, like being able to scale down. I thought scaling down would be for more local development purposes like Minikube, as opposed to retail edge, but the ability to kind of scale down and not have a huge footprint was definitely a design goal. So we didn't want to have several stateful components like a database and a message bus and a cache and maybe something else. We wanted to just be able to run with the one key value store. So that informed the approach we took to the system design. So if you're designing with different constraints, like it's always going to run on cloud and doesn't have to keep up with real-time events and things like that, you probably would make different decisions. But, I still think there are some lessons learned about what constitutes a control plane and what needs to be part of a control plane that could be taken away from the project. So I think there's some parts of the design that people could take lessons from. There are a bunch of good blog posts and presentations and things about the Kubernetes design that I think could be informative if people are looking to build their own systems for a different purpose.
A few years back, I maintained the operator framework for Elixir and Erlang. And just being able to go in, reading the docs is one thing, but going in and getting familiar enough with Kubernetes from the ground up, right? Or even going through, Kelsey's Kubernetes the hard way. There is so much interesting stuff in just the way that it was designed and layered together that I think is just great things to be familiar with, to apply other places in your development processes. There's a lot of really interesting ways that things were designed, and the key value store at the center, it seems like a simple choice, but it empowered so many other ways, like you're saying, being able to run it at the edge. I know somebody who's putting it on satellites currently, it's kind of everywhere, and it's empowered by these simple, clean primitives that we have at the base.
Yeah, but if you needed to scale it to 100 million instances or something, you probably wouldn't design it that way. So, so you kind of have to understand what the design constraints were and what envelope it was intended to fit within. And then you can decide, well, my requirements are different in this way, so I need to make this kind of change to the way the system is designed. One aspect of the design was that we assumed that most of the entities would be updated frequently. So if most of the entities are updated frequently, then the controllers need to have them in memory. So there were things like that. Whereas if, it's like a retail site's product catalog, you would probably design it differently. Maybe interesting as a design case study at some point.
Yeah. Awesome. And is there any advice that you would give for just people getting into the space, into operations, distributed systems? What advice would you give for somebody there?
Definitely use the managed service if you can. That's the easiest way. Also, familiarize yourself with the failure modes, so you don't have to debug them when it's critical. Right. So I know in the early days of Borg, when I was on call, debugging production when production is down is not super fun. It's easier to to kind of do it in a more isolated, less pressured scenario. So, I think at this point, a lot of the failure modes are pretty well known, and some of them are preventable, but in any case, like understanding the things that are likely to go wrong before they kind of do go wrong in a critical situation, I think is the first thing I would recommend. So I think that's one of the reasons why Kubernetes the hard way resonated with a lot of people, is it helped them understand, okay, what are the components? How do they interact? How do the components stay running? What can go wrong with those components? I was actually looking back through the Kubernetes 1.0 milestone issue list, and a lot of the things we were working on, because we wanted Kubernetes to be usable in production. So we had run a lot of integration tests and a lot of users kicking the tires and things like that. But we had cases where dead Docker containers could pile up. And, they would just continue piling up until the node disk filled up, right? So those seem kind of trivial, but, those basic things like log rotation and cleaning up dead containers and restarting components and things like that. That was a lot of the kind of the productionization work we did leading up to Kubernetes 1.0. So just familiarizing yourself with those kind of basic mechanics if you're running your own cluster, especially. What can go wrong if this component doesn't restart, or this disk fills up, or this the container registry becomes inaccessible, or some random failure mode like that.
Yeah. Is that milestone checklist? Is that public?
I checked. It hasn't been deleted off of GitHub.
Oh, awesome. Okay. I'm gonna put that in the show notes. That'll be a fun one to review 10 years in. Awesome. Well, I really appreciate the time coming on the show today. Thanks so much. Where can people find you online? I
am B Grant on Twitter, LinkedIn, GitHub, and Medium.
Nice. I love it. Uniform. Well, thanks so much. I really appreciate the time.
Yeah, it was fun. Thanks.
Thank you for listening to this episode of the Platform Engineering Podcast. Have a topic you would love to learn more about? Let us know at Cory@massdriver.cloud. That's CORY@MASSDRIVER.cloud. Catch you on the next one.